So today we're just going to cover expectation, and we've actually kind of already touched on expectation at the end of the last unit. If there are n trials of an experiment and an event has a probability of p of occurring in each of the trials, the number of times we expect the event to occur is n times p. We've already done NP. I talked about a field goal kicker. It's got, like, you say, if you got a 90% chance of kicking it and getting it in through the goalposts, and you kick 100 kicks, you expect 90 of them to go through, because that's 0.9 times 100. It's just n times p, the number of trials times the probability. So you would think, oh, expectation should be really, really easy, right? Each time a soccer player kicks for goal, he has a 3/4 chance of being successful. In a particular game, he has 12 kicks for goal. How many goals would you expect him to kick? Well, we would expect E of x to equal n times p,
You're
or
not sharing your screen.
I'm not sharing my screen. Shame. What a shame. Now I'm sharing screen. Okay, so n times p, where n is the number of trials. That didn't look good. And p is the probability it occurs, 3/4. And then you just go, okay, 12 times 3/4. That's, yeah, that's 9. There you go. So you would expect him to get 9 goals. That seems really easy, right? So what am I worried about? Well, the expected outcome of the random variable x is the mean result, or mu. In general, the expectation of the random variable x is, you say E of x equals mu, the mean of the system, which is equal to the sum of the what's it called? The variable times its probability. Sorry, I had a senior moment there for a second. So whatever the variable's value is times the probability it occurs. And then you add all those up, and that is the expected value of the system. Does the expected value have to be part of the system? No. Just like how the median doesn't have to actually be part of a set of data, the expected value of a system does not even need to be possible. It does not need to be part of the actual system. For example, the expected value of rolling a die is like 3 and change. It's like 3.5 or something like that. That's impossible, but that is the expected value. A magazine store recorded the number of magazines purchased by its customers in 1 week. Hey, that sounds familiar. 23% purchased 1 magazine, 38% purchased 2, 21 purchased 3, 13 purchased 4, 5 purchased 5. I feel like we just did this. We did. Yeah. We did it yesterday. We drew, I think for this one we did this one was the one we did a bar graph for. Remember that? And I think we found the mean and the mode. Not the median, excuse me, in the mode. We did this yesterday. Okay, we didn't find the mean specifically. That's because the mean is an expected value. Today, we're going to record these results in the probability table that I drew for you, and we're going to find the mean of the data and explain what that mean means. What a weird thing to say. Okay, so xi, ooh, that's better. Yeah, we're going to explain what the mean represents. Thank you. So xi are the possible outcomes, and the possible outcomes are the number of magazines that these people purchase. So 1, 2, 3, 4, 5. Pi is the probability that that event occurs. So the probability a person buys 1 magazine is 0.23. Probability to buy 2 magazines is 0.38. Probability to purchase 3 is 0.21, 0.13, 0.05. You know what's not on this table? A product row. Do you remember we were doing the tables and I had you creating a product column? Okay, it's the same idea. We need a product column. So this is going to be XIPI. And we'll just go ahead and extend this table. And you multiply straight down. So 0.23, that was easy. 0.76, 0.63.52 and 0.025, I think. Yeah. Those aren't on my paper, so I was just doing those real quick. Right. Well, the expected value of this system would be the sum of the XIPIs. So E of X, the mean number of magazines purchased, which is, oh, that's what it represents. The mean number, the average number of magazines purchased.
Mr. McCutcheon, 5 times 0.05 is 0.25.
I knew that. I did. I swear I did. The person behind me that said I was right, I was just testing them. Sorry, 0.25. Boink. There we go. Good shot. Good shot. All right, so we're going to add these things up. I'll show the work. So it's just 0.23 plus 0.76 plus 0.63 plus 0.52 plus 0.25. And what you get is that E of X is 2.39. That's the expected value. So what does that represent? See, what we did was we took the possible outcomes, we multiplied by their probabilities, which was the same thing we did for finding the product column, isn't it? Where we took the value or the mid-interval value of group data multiplied by the number of times it happened. It's the same idea, just used for different materials. So anyway, you take the possible values, multiply them by the probability they occur, add all those up, and you get 2.39. And what does that represent? 2.39 is the average number of magazines. Average number of magazines, too lazy to write that word, purchased per customer is, is 2.3. Okay, the board just had a stroke. Let's try again. Is 2.39. Kennedy, what can I do for you? No. It's already technically been divided. It already worked itself out this way. That's what the probabilities are. The probabilities are where the divisions are occurring. So, yeah, this is the average number of magazines that were purchased per customer, which is an impossibility. There is no way that you're buying 2.39 magazines, but it doesn't matter. That's important information to a magazine shop, isn't it? Because if you know the average number of magazines purchased is 2.39, you can determine a sale price to figure out what your expected profits would be in order to pay your employees and your bills and yourself. So that is why this is powerful information to have. And that's going to do it for expectation. We'll use it tomorrow to talk about how fair games are built.